Hello, engineering statics. In this mini lecture, I'll be discussing moment about a point. So at this point in your study of statics, you should be very familiar with Newton's second law, force equaling mass times acceleration. And since in the study of statics, we definitely don't want acceleration, we have a situation where the sum of all of the forces on a body, otherwise known as sum of the forces or F net, has to be zero. The acceleration in this expression basically corresponds to a body moving in a straight line versus any of our three coordinate axes. So it can go any which way, and those acceleration directions are the ones we don't want to happen. So that's what we're preventing when we make sure that the sum of our forces is zero. So we're preventing what's known as translational acceleration. So the blob can't basically translate, so it moves over here, it moves over here. We have effectively prevented that by summing the forces to zero, and so our body with mass can't accelerate. Now what we haven't addressed is that rigid body rotating about an axis, about any axis. Can it spin on a given axis? So we've said the forces have to be zero, but we haven't explicitly looked at whether or not we're going to have this body rotating. So rotational motion is a little bit different than translational motion. And there is, lucky for us, an analog to Newton's second law for rotation, and it says moment, otherwise known as torque, you may see it as tau, is going to be equal to the moment of inertia of a body, which is kind of an analog to mass, times the rotational acceleration. So, and it will also have a vector. So this is our rotational analog. If we're in statics, we don't want something accelerating rotationally any more than we want it accelerating translationally. So if you imagine like you've got a dam holding back a lot of water, if it twists, it can shift on its abutments and release all the water. And that's kind of what happened with a few of the noteworthy, very deadly dam failures like St. Francis in Los Angeles. So we don't want any translational motion and in statics, and we don't want any rotational motion. We don't want any rotational acceleration. Well, we're not going to take the moment of inertia away from our bodies. We're not any more than we're going to take away their mass. So just like we had to make the sum of the forces zero, we have to make sure that the sum of the moments equals moment net equals zero. So that brings about two conditions of equilibrium for a rigid body as opposed to a point. Of equilibrium. If we don't have a point, if we've got a rigid body that can rotate, where we can exert a force on one side and cause it to spin, now if we want to keep it in static equilibrium, we have to say the sum of the forces in the x, y, and z directions all have to sum, each one of them has to be zero, and we have to make sure that the moments or torques in each orthogonal direction is zero. Then nothing is going to accelerate translationally. It's not going to move side to side, and it's not going to accelerate rotationally. No alpha, it's not going to spin. So that's why we care about moment. That is part of our fundamental criteria for equilibrium. So you can think of F equals ma, m equals I alpha. So we're going to make sure the m is 0, just like we made sure that the F was 0. Okay, so now that we know that, we know why moment is important. It's what causes things to rotate. Now we can think about, well, what is it that actually can bring about moments? Forces bring about moments, actually. Forces acting at a distance. So that is, in fact, the definition of a moment. So we actually do need, we may sometimes represent a moment as forceless, as a pure applied moment. But at some point, if you go far enough back, there is a force somewhere that caused that moment. So for our purposes, moment is defined as the distance from the point about which we care about, our radius vector from the point of interest to the line of action of the force crossed, this is the vector cross product, into the force vector. So we got our body, we got some point of interest on our body, we got a force acting on that body somewhere. We'll call it a contact force. We'll call this point A, and there's a line of action that we can draw that force acts on. All forces have a line of action. And it's defined by their unit vector direction, which we all know how to calculate, which is great. So if we take a vector and construct one and say, okay, I'm going to draw a vector, a radius vector, or position vector from my point of interest, point A, to any point on that line of action of my force, and then take the cross product of this radius vector with the force vector, I am going to get the moment of this force about this point. So moment about a point. So that will tell me basically how hard that force is causing a twist around point A. So it's going to want to spin this body in the counterclockwise direction. And in fact, the vector direction for that moment is going to end up pointing straight out of the board. Okay. So this immediately brings us to the definition of the cross product. To calculate a moment, we got to know, well, okay, what is this cross product? Well, it's easy. Those of you who have already learned this in a vector algebra class, this is a review, and we've already covered the vector dot product, otherwise known as the scalar product. So this is kind of similar, but with one real key difference. The vector cross product has a geometric definition, and we'll look at the two vectors that make up moment. So R cross F can be defined as the magnitude of vector R times the magnitude of vector F times the sine of the acute angle between them. RF sine theta. Okay. So if I'm looking at the sine of this angle, basically I can draw a right triangle here. Here's my hypotenuse. This is theta. So sine theta is this quantity right here, which we'll just call d. So d happens to be the perpendicular distance between our point and the line of action of the force. So one of the things that the cross product did for us is, if we want to rearrange the terms over here, it basically took the portion of our radius vector that was perpendicular to the line of action of force and created it for us. That sine term basically says take the part that's perpendicular, just like the dot product cosine theta said just take the part that's parallel. So the dot product and the cross product are totally analogous in that they take either the part that's parallel, a part of a vector that's parallel to another one, the dot product, or the part that's perpendicular to another vector, the cross product. So the cross product basically gives us an expression for the magnitude of the force, we'll just write it without the letter or the bars, meaning magnitude, times d over here, which is defined as this. And if anyone looks back in physics, you might see an expression for torque equaling force times distance, where it was implied that that distance was always perpendicular. Well, that perpendicular distance was brought to you thanks to the vector cross product. So why don't we always just use the geometric perpendicular distance? We will when it's easy to get at. In a lot of cases, things will be obviously perpendicular or provably perpendicular, or we can use a little trig to find the perpendicular component. But in other cases, that perpendicular distance isn't nearly as easy to find, and we may have a coordinate grid with a collection of points, and our forces and our positions may be defined by those points. And so it is much easier to use the algebraic definition of the cross product rather than the geometric expression with the cosine theta. It ends up meaning the same thing. So let's do a little example. Let's go back to our friend, the box sitting on a coordinate axis. You've very likely done some of these in some homeworks. So we'll define our 3D coordinate axes, our favorite axes, and we're going to draw a little shape of interest. Nice parallelepiped, 3D rectangular something or other. Buildings, lots of things kind of take this shape. This is not great artwork, but it doesn't have to be. So we'll assume that this direction is 3 meters, this is 1 meter, and this is 2 meters. And we're going to consider moments of some force about the origin. And we're going to look at a force that has a line of action between points A and B. So I'm going to try to draw a little dotted line, which is one of the body diagonals of this shape. I'm going to say there's a 10 Newton force that is being exerted along that line of action. So we're going to ask a question here. What is the total force and total moment about the origin So that's going to be our question we'll ask ourselves for this system. Okay, well, let's say we're in statics, so our little box here is rigid. So the total force is really easy. Total force, 10 newtons, because wherever we apply that force, we're applying it through the rigid body. That body is rigid, it's not going to deform, so it's going to transfer all of that force to any other point. So this happens to be the net force on the body, and so the force exerted anywhere on the body is the net force. It's obviously not in static equilibrium. It's going to start accelerating, but we can always add another force to keep it from doing that. In fact, we could calculate what we would have to. But we also want to keep this box from rotating somehow, or we want to know how much it's rotating. We want to know the total moment. Maybe we got to apply something to stop that. So we need to calculate that. Well, let's, gosh, how would we do that? I'm going to reach for my friend, my cross product moment. M equals R cross F. Okay, now all I need to do is get a vector expression for the radius, which is going to be, since it's about the origin that I care, so I need a radius vector from the origin to any point on the line of action of that force. And being that I like to keep life simple, I'm going to use this radius vector, because point A is on the line of action of force. And so I'm going to use a radius vector that's defined as I hat. All right, I go from 0, 0, 0 to 1, 0, 0. Point A is at 1, 0, 0 because this dimension is 1 meter. So my radius factor is I hat. There's, it's not going up, it's not going over. So, okay, there's one down. Check. Now I need a force vector. I know its magnitude, it's 10 newtons, but now I can say that this equals 10 newtons times a unit vector in the F direction. So now I need a unit vector again. Good thing I know that this line of action goes through points A and B, because that makes it pretty easy to construct a unit vector. So I'm going to go over and kind of do that on the sideline, because I'm going to need that to calculate my cross product. So F hat, I can calculate it by first getting a full position vector that would take me from point A to point B. So I can do that by basically saying I need a vector AB, and then I'm going to divide it by the magnitude of AB, right, to divide out the length. So I can get the numerator by subtracting the coordinates of point B, or taking the coordinates of point B and subtracting the coordinates of point A. So coordinates of point B are, I'm just going to write like this. So B is at 0. It's at 3 meters in the j hat direction, and it is 2 meters in the k hat direction. And I'm going to subtract, so this is point B. I'm going to subtract point A, which is 1 meter, and 0, 0. So I'm going to end up with a vector A to B. I am going to end up with negative 1 meter I hat plus 3 meters j hat plus 2 meters k hat. And then the length of AB, we can use Pythagorean theorem. 1 plus 9 plus 4 square root of 14. And these are all meters squared. So square root of 14 meters squared. Okay, so my unit vector F is going to be, I am going to factor out all my scalars. I'm going to have meters up here, and then I'm going to have square root of 14 meters squared. And then I'm going to be left with negative I hat plus 3j hat plus 2k hat. And I can cross out meters. Okay, I have no units. I could go back and check that this has a length of 1 if I wanted to be really sure. Okay, so I can send 10 newtons down that. That's my magnitude, so what I'm going to end up with is 10 newtons divided by square root of 14 times negative I hat plus 3j hat plus 2k hat. Okay, so now I have the task of calculating the actual cross product, and that's something that we haven't said yet. We haven't gone through how to do that. So I'm going to give myself a little bit of space here and rewrite some stuff. So we're going to go ahead and calculate our moment, and we're going to go over, do a little review of the algebraic calculation of the cross product. So I'm going to rewrite my expressions for R and F. So I'll be ready to cross them. I hat, and so F, this is really in meters. Newtons. I'm trying to keep my units with me as much as possible because that helps me remember if I did things right, because I know I need to have moment in units of Newton meters. So I like to do that, but when we're doing a lot of vector algebra, sometimes it gets very cumbersome to write a lot of units. So I'm going to kind of keep them out here, and I may put them over to the side and do a units check first. So I'm gonna, all of this was just giving me a vector F, getting my direction for that force in terms of I hat, j hat, k hat. Now this is what we're going to do is equivalent to magnitude of R times magnitude of F times sine of the angle between them. But we're going to go through the vector algebra way of calculating the cross product because that sine theta is not so easy to spot. If you had a real good eye for 3D geometry, you might be able to get it, and some people are better at that than others. But by turning the crank, so to speak, through the cross product, we can get it every time, and furthermore, we can program a computer to do the cross product for us, which is even nicer. Okay, so we're going to do two different methods for calculating the cross product in 3D. And so I'm just going to write, we're going to actually do R cross F. And for the moment, I am going to leave off the meters and the 10 newtons divided by root 14 because we know that we can distribute a scalar over a cross product, a vector product. That's one of the great properties of vector products. So basically I can do like a scalar alpha times A cross B equals, alpha times vector A times crossed into alpha times vector B. So we can basically factor those out. This meters will end up getting multiplied by everything over here, and likewise. So we can basically do the scalar part of the multiplication on the side and not have to involve it in our math. If you included it, you would find that it did carry over. So we're just going to do I hat times the simpler part of vector F. So the fastest way most people use, and it requires keeping things lined up a little bit better, is called the determinant method. And for that, you start by writing all of your unit vector designations on your first line of your determinant, and then you repeat the first two over to the right. Then you go ahead and write your first vector, which is going to be r, that you're multiplying. In this case, we've got 1, 0, 0, and then you repeat your I hat direction and your j hat, which will be 1 and 0. Then you do your second part of the product, which in this case is -1, 3, 2, and then -1, 3. Now I'm going to use a different color. Now you draw diagonal lines and you multiply everything on that line and then sum up all of those products over here. So I'm going to have I hat times 0 times 2, which gives me 0 I hat, or just 0. I have j hat times 0 times -1, which basically gives me 0 again. And I have k hat times 1 times 3, which gives me 3 k hat. Okay, now I'm going to multiply going with diagonals in the other direction. Use a different color because I can. It kind of pays to write these as neatly as possible. It's kind of easy to get that mixed up if you don't. And this time we've got a negative sign out in front of our products that we're going to add up. The reason for this is evident if you do what's called the FOIL method, which I can show you later, or that I demonstrated in a live lecture. But basically you've got a negative sign out here because what you're doing effectively when you do the full matrix multiplication is you're ending up multiplying unit vectors, you're cross multiplying, you're doing the cross product of these different unit vectors, and some of them end up being negative. So the cross product follows what's known as the right hand rule, which I'll demonstrate because I have a camera. So if I stick my fingers in the direction of my first vector, so this would be the r direction, and I curl them in the direction of f, so if I had a force going in the direction of my fingers and then the force, or the radius in the direction of my fingers, and the force direction was towards my face, I would curl my fingers towards f, which is pointing in my face, and then my thumb is pointing in the direction of the net moment. So it would be twisting. So that's known as the right hand rule, and it's all over physics, anything with a direction. But that right-handedness is the convention that comes from the vector cross product. So anything that is actually the result of the vector cross product is going to follow the right hand rule in terms of which direction that vector product is going to be pointing. And so that's that action of that directionality on the unit vectors that are actually getting multiplied as we go through this determinant method is why you got that negative sign out there. Kind of fun, but you don't need to know it to just manipulate it. So we'll just continue here. You've got your k hat times 0, so that's going to give you, 0 k hat. You've got I hat times 0, 0 again. And now we have 2 times j hat. Okay, so we got a negative sign there. So we can add all this up. So we're going to have -2 j hat plus 3 k hat. Okay, so our moment is in the jk plane, basically. So it's somewhere in this plane. It doesn't have an I hat component, so there's nothing sticking out in this direction. So the twist is being exerted. Basically, the body's going to want to rotate about like this. I I will sometimes try to guess at twisting clockwise, counterclockwise directions, but basically one of the reasons that we calculate the cross product this way and we designate a vector coordinate direction for basically the twist axis, which is what the vector moment is because it's really hard to envision exactly which way things are rotating. So I'm not going to say any more about, kind of empirically how it's twisting. But this is our I hat times what's in these parentheses. So we need to multiply this by, to get our full R cross F, we have to multiply that by 1 meter times our 10 newtons over root 14 that came from our magnitude of force and our achievement of our force unit vector, and now we're going to have our cross product portion. And that's it. That's the moment of that force about that point. And most importantly, notice it's in Newton meters, which is the proper units for moment. So we would be done. We could multiply it out and get a vector expression. We could distribute this 10 newtons and get maybe a decimal designation. This works too. It's very important we have our units there. So that's it. I'm not going to demonstrate the FOIL method. It's pretty long and tedious, but if you forget how to set up the determinant, I'll just start it really quick here. And it's a little bit easier with the I hat. With the FOIL method, we use our real basic algebra first, inner, outer, last, and we just multiply each component by the other. And in this case, this is a great demonstration of how we multiply the vectors together using our vector rules and the scalars together with scalar rules. So we have I hat times negative I hat, which will give us a negative 1. Scalar 1 times scalar negative 1 is negative 1. And then we have I hat cross I hat. Then we have 1 times 3, which gives us 3. I hat cross j hat. And then we have 1 times 2, which gives us 2 times I hat cross k hat. Very important we keep the order because the cross product, unlike the dot product, is not commutative. So I hat cross I hat is 0 because it's parallel to itself, and of course the cross product only takes the perpendicular portion, so that whole term goes away. Now we apply the right-hand rule to get the result of this. So if you take the x-axis and cross it into the y-axis, the result is the positive k-axis. And if we take the x-axis and cross it into the positive k-axis, we get the negative j hat. You kind of can bend your wrist a little bit trying to apply the right-hand rule, and so lo and behold we get negative 2 j hat plus 3 k hat. So I could make an argument that the FOIL method might have been just as fast as the determinant, but it's good that we got the same answer. So again, just like we ended up having the constants being multiplied and coming out, remember we had a 1 meter being multiplied by everything, and we had a 10 Newton divided by root 14 all the way through here, so we would end up having our scalar portion. So that is it. We have determined the moment about a point exerted by a force and applied our R cross F cross product in 3D and avoided a gnarly geometry problem. So that is it for this mini lecture, and enjoy calculating some moments about points.